Right now, without anyone aboard it feeling a thing, the Milky Way is falling through space at about 2.2 million kilometers per hour, carrying our sun, our solar system, and every star in the night sky along with it. It is heading toward a patch of sky where nothing unusual seems to be, and where, in fact, almost nothing can be seen at all. A dust-choked band of our own galaxy hides the true destination from direct view. Astronomers gave the source of that pull a plain, almost startled name, the Great Attractor. This is the story of how that name came to be, how decades of quiet, patient work forced a hidden structure into view piece by piece, and how it ultimately turned out to be a signpost pointing to something even larger, holding the very supercluster of galaxies we now call home. In 1965, two radio engineers in New Jersey picked up a faint hiss in their antenna that would not go away, no matter where they pointed it. That hiss turned out to be the afterglow of the Big Bang itself, cooled over 8 billion years into a bath of microwave radiation that fills every direction of the sky almost perfectly evenly. Astronomers call it the cosmic microwave background, the oldest light in the universe, released when the cosmos first became transparent enough for light to travel freely. For a few years, that word almost seemed to be the whole story, evenly, uniformly, the same temperature everywhere anyone looked. Then, in the 1970s, instruments sensitive enough to catch a difference of a few thousandths of a degree found something odd. One side of the sky was very slightly warmer than the other, and the opposite side was very slightly cooler, in a smooth pattern astronomers call a dipole, as though the sky itself had been tilted. The explanation was not that the early universe had been lopsided. It was that we are moving. Light gets slightly compressed, and so slightly hotter, in the direction an observer is heading, and slightly stretched, so slightly cooler, in the direction behind them, the same effect that raises the pitch of a siren approaching and drops it as it passes. By measuring the size of that temperature tilt, astronomers could calculate a speed. The solar system is moving at around 370 kilometers every second relative to the frame in which the background radiation would look perfectly uniform. Once that motion is corrected for the Sun's own orbit around the center of the Milky Way, a further number emerges. The Milky Way galaxy itself, carrying every star in it, is moving at roughly 600 kilometers per second relative to that same cosmic frame. That works out to about 2.2 million kilometers every hour, a speed at which a trip to the moon would take under 11 minutes. A speed like that demands a reason. Nothing in the universe accelerates for free. 2 decades earlier, the American astronomer Vera Rubin, working with Kent Ford, had already begun turning up a related puzzle while surveying the motions of nearby galaxies. Galaxies do not sit still relative to one another. Space itself is expanding, carrying galaxies apart in what astronomers call the Hubble flow, a smooth, predictable recession where more distant galaxies appear to recede faster in direct proportion to their distance. But when Rubin and Ford measured galaxies in different directions across the sky, the recession speeds did not fit the smooth pattern evenly. Some galaxies appeared to be moving faster than the general expansion predicted, others slower, in a pattern that itself pointed toward one direction more than others. This extra motion, layered on top of the uniform stretching of space, is called peculiar velocity, and it is the fingerprint of gravity from something with enough mass to actually accelerate galaxies, not just carry them along with the expanding fabric of space. Put the two findings side by side and a single picture starts to form. The Milky Ways fall through the cosmic frame, and the peculiar velocities Rubin measured in nearby galaxies both trace back toward roughly the same stretch of sky, in the general direction of 2 southern constellations, Centaurus and Hydra. Whatever was out there had enough gravitational pull to accelerate not just our galaxy, but apparently many of our neighbours as well, all being drawn along a shared path. No visible concentration of galaxies in that direction seemed remotely large enough to explain a pull that strong. The mystery had a direction. It did not yet have a cause anyone could point to and see. The scale of the puzzle only sharpened as more precise measurements came in through the late 1970s and early 1980s. Different teams, using different methods, kept arriving at compatible numbers for the size and direction of the flow, which ruled out the simplest explanation, that it was some kind of measurement error confined to one telescope or one team. Whatever was pulling on the local group of galaxies, the modest cluster of a few dozen galaxies that includes the Milky Way and Andromeda, was real, and it was big enough to move an entire galaxy supercluster's worth of matter as a coherent unit. Astronomers were forced to accept an uncomfortable conclusion, An enormous concentration of mass, easily rivaling many known galaxy clusters combined, appeared to sit in a direction of the sky where no such concentration had ever been catalogued. Not every astronomer accepted the Rutherford result immediately. Some early critics argued the sample of galaxies used was too small or too biased toward one part of the sky to trust the direction confidently. That skepticism was healthy and, in hindsight, useful. It pushed later researchers to build far larger and more careful surveys before claiming they had found the source. The caution mattered because what came next was not a single confirming observation but nearly a decade of accumulating evidence from independent groups, each converging, slowly and reluctantly, on the same unlikely answer, one that happened to overlap almost exactly with the one part of the extragalactic universe that our own galaxy makes nearly impossible to see. The Milky Way, the galaxy we live inside, has a shape most people picture correctly, a flattened disk of stars, gas and dust, spanning roughly 100,000 light-years, with our solar system embedded in one of its spiral arms about halfway out from the centre. Living inside that disk gives us a magnificent view of the galaxy from within, the pale river of light called the Milky Way that stretches across a dark night sky. It also gives us a serious problem for any astronomer trying to look past our own galaxy toward the rest of the universe. Looking toward the flat plane of the disk means looking through a very long path of gas and dust, sometimes tens of thousands of light-years of it, before any light from beyond can reach a telescope on Earth. Dust in space is not like household dust. It is made of tiny solid grains, often just fragments of carbon and silicate minerals, no bigger than particles of smoke, formed in the outer atmospheres of dying stars and drifting through interstellar space ever since. A single grain is nothing, but spread across tens of thousands of light-years in the dense midplane of a spiral galaxy, those grains absorb and scatter visible light so effectively that entire galaxies, sitting directly behind the Milky Way's disk, can vanish from view entirely, as thoroughly as if a curtain had been drawn across that patch of sky. Astronomers had noticed the effect long before they understood the cause. 19th century sky surveys kept turning up a conspicuous band, roughly following the plane of the Milky Way, where far fewer distant galaxies were counted than anywhere else on the sky. In 1878, the writer and astronomer Richard Proctor gave that empty-looking band a name that stuck, the Zone of Avoidance, as though the galaxies themselves were shying away from it. It took decades more before astronomers understood that the galaxies were there all along, simply hidden. The Zone of Avoidance covers a serious fraction of the observable sky, on the order of 20%, blotted out not because nothing exists there, but because our own home gets in the way. And it happens to run directly through the same stretch of sky where the peculiar velocity measurements of the 1970s pointed, the same general direction, towards Centaurus and Hydra, where something massive appeared to be pulling the local group off the smooth path of cosmic expansion. The single region of the universe astronomers most needed to examine closely was also the single region their normal tools could least see into. It is a strange kind of cosmic irony. The mystery hid partly behind the very galaxy asking the question. Working around a wall like that takes more than patience. Visible light, the kind human eyes and ordinary telescopes are built to use, is scattered badly by interstellar dust, but light at other wavelengths behaves differently. Infrared light, with a longer wavelength than the dust grains are efficient at blocking, passes through far more easily. The same reason warmth from the sun still reaches the ground on a foggy morning, even when visibility for the eye drops to a few meters. Radio waves, longer still, pass through interstellar dust, almost as if it were not there at all. Both of those facts would eventually become the tools that let astronomers see past the Milky Way's disk. But, in the years immediately after the mystery motion was confirmed, the technology and the sky surveys needed to exploit them at scale did not yet exist. For a while, the only path forward was to work around the edges of the hidden zone, mapping everything that could be seen just outside it, and using statistics to guess at what the missing middle might contain. Even where the dust thinned rather than fully blocking the view, distances remained hard to pin down. Simply having a redshift, the stretching of a galaxy's light caused by cosmic expansion, was not enough by itself, because a galaxy's redshift is a mixture of the smooth Hubble expansion and any peculiar velocity layered on top of it, the very quantity astronomers were trying to isolate. To disentangle the two, they needed an independent way of measuring a galaxy's true distance that did not rely on its redshift at all, so the peculiar motion could be calculated as the leftover difference. That requirement, more than any single observation, would define the entire next phase of the search, one a small team of astronomers took up in the mid-1980s when they set out to systematically measure the distances and velocities of galaxies across the entire region implicated by the earlier peculiar velocity work, dust or no dust. Their result would give the mystery its name. By the middle of the 1980s, 7 astronomers scattered across different institutions in the United States and Britain decided to attack the mystery together rather than separately. Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Robert Turlevich, and Gary Wegner. Colleagues, only half joking, nicknamed the group the Seven Samurai, after the classic film about 7 warriors banding together against a common threat. Their target was not a threat exactly, but it was every bit as elusive, an unseen mass whose gravity was reaching across hundreds of millions of light-years to steer entire galaxies off course. Their tool was a clever piece of physics rather than a bigger telescope. Elliptical galaxies, the smooth, egg-shaped galaxies with no obvious spiral structure, have a well-established relationship between how fast their stars move internally and how bright the galaxy truly is. The faster the internal motion, the more massive and luminous the galaxy tends to be, following a pattern astronomers call the Faber-Jackson relation, later refined into what is known as the dn-sigma relation. Because that relationship links an internal property, the speed of stars inside the galaxy, to the galaxy's true brightness, it gives a way to estimate a galaxy's real distance that has nothing to do with its redshift at all. Measure the internal stellar speeds, work out the true luminosity the relation predicts, compare that to how bright the galaxy actually appears from Earth, and the difference reveals the distance, independent of cosmic expansion entirely. With that independent distance in hand for each galaxy, the team could finally do what nobody had done at this scale before. Compare each galaxy's true distance to the recession velocity implied by its redshift, and see whether the two agreed. If the universe's expansion were the only thing moving these galaxies, the two numbers would match for every galaxy, in every direction. They did not. Across roughly 400 elliptical galaxies, spread through a volume of space extending across a large fraction of the nearby universe, the team found a coherent pattern. Galaxy after galaxy showed a peculiar velocity, above and beyond the expansion, all pointing in a broadly consistent direction, all flowing as though pulled toward a single common destination. The 1987 and 1988 papers describing the result gave that destination its lasting name. They called it the Great Attractor, deliberately plain language for something they still could not directly see or fully characterize. Their best estimate placed the source of the pull at a distance of roughly 150 to 250 million light-years from the Milky Way, almost squarely inside the Zone of Avoidance, the same dust-hidden stretch of sky the earlier peculiar velocity work had implicated. The estimated mass required to produce a flow of that coherence and size across that much of the surrounding universe was extraordinary. On the order of several times 10 to the 16th solar masses, tens of thousands of times the mass of the entire Milky Way, spread across a region hundreds of millions of light-years wide. To put that distance in a more human frame, light now reaching Earth's telescopes from the far edge of the region the 7 Samurai identified as flowing together left its source somewhere between 150 million and 250 million years ago. On Earth, that stretch of time reaches back past the first dinosaurs, past the earliest mammals, into the Triassic period, when the continents were still fused into a single landmass. Every galaxy in that flow has been drifting toward the same gravitational center for a span of time longer than the entire age of the dinosaurs, at a speed too slow for any single human lifetime to notice, yet fast enough, over hundreds of millions of years, to visibly separate the flowing galaxies from the smooth backdrop of cosmic expansion around them. The 7 Samurai result was immediately controversial, and reasonably so. A claim this large, resting on a distance-measuring technique with real scatter and uncertainty, needed independent confirmation before the astronomical community would treat the Great Attractor as more than a suggestive pattern in one team's dataset. That confirmation would come, gradually, from other groups using other methods over the following decade. But the name had already stuck, and so had the challenge it implied. Something enormous was sitting largely inside the one region of sky the Milky Way's own disk made hardest to study directly. Gravity does not care whether the mass producing it can be seen. A galaxy drifting past a massive but completely dark clump of matter feels exactly the same tug it would feel from an equally massive clump of glowing stars. That simple fact is what let astronomers turn the peculiar velocities the Seven Samurai measured into something more like a map, without ever needing to see the thing doing the pulling directly. By the late 1980s, astronomers already had strong, independent evidence that most of the matter in the universe does not shine at all. Vera Rubin's earlier work on individual spiral galaxies had shown that stars near the outer edges of a galaxy's disk orbit far faster than the visible matter the stars and gas astronomers can actually see could account for. Something extra, invisible at every wavelength anyone had tried, had to be supplying the additional gravity, holding those fast-orbiting outer stars in place. Clusters of galaxies told the same story on a larger scale. The individual galaxies inside a cluster move fast enough that, without a great deal of extra unseen mass binding the cluster together, they should long ago have drifted apart. Astronomers named this unseen material dark matter, and by the calculations converging from multiple independent methods, it appeared to outweigh the ordinary visible matter that makes up stars and planets by roughly 5 to 1. Whatever was creating the Great Attractor's pull did not need to be made of anything glowing at all. It only needed mass of any kind in enough quantity. That reframing let astronomers attack the problem mathematically rather than only observationally. In the early 1990s, the astrophysicist Avishai Dickel and collaborators developed a technique, given the working name potent, that used the equations of gravitational physics in reverse. Ordinarily, a physicist starts from a known distribution of mass and calculates the gravitational field and the velocities it would produce. Deckel's team ran the calculation backward, starting from the measured peculiar velocities of thousands of galaxies scattered across a large volume of the nearby universe. They reconstructed the underlying pattern of mass, both visible and dark, that would be required to produce exactly that pattern of motion. The technique could not see the Great Attractor directly. It inferred its presence, its rough shape and its approximate mass entirely from the way galaxies around it were moving, the same way a geologist can infer the shape of a riverbed from nothing but the pattern of a river's current on the surface, without ever draining the water away to look. The image that emerged from these reconstructions was not a single dense point, but something closer to a broad, gently sloped basin in the fabric of surrounding space, a wide gravitational depression toward which galaxies across an enormous volume were slowly sliding. Individual galaxies caught in that basin behave less like objects falling directly toward a target, and more like driftwood carried along a slow, wide current, drawn steadily toward a distant, still largely unseen low point in the terrain, gathering speed only as the terrain steepens near the middle. That image would turn out to matter a great deal for how astronomers eventually understood the full scale of the structure, because a broad basin, rather than a single localized clump, hinted that the true source of the pull might be considerably larger and more spread out than the original Seven Samurai estimate had suggested. None of this reconstruction work was free of controversy. The mathematics behind potent and similar techniques required smoothing over gaps in the data and made simplifying assumptions about how closely galaxy motions track the underlying mass, assumptions that different research groups debated through much of the 1990s. Independent surveys sometimes returned overlapping but not identical pictures of the basin's exact shape and total mass. What nearly every method agreed on, however, was the existence and rough location of a large-scale, coherent flow centered somewhere in the direction of the constellations Centaurus and Norma, still mostly hidden behind the Milky Way's own disk. The next real progress would not come from more clever mathematics applied to the same visible light data. It would come from finally building the tools to see straight through the dust in the way ahead. Solving a hidden mass problem sitting in a nearly invisible part of the sky required the astronomical equivalent of a different pair of glasses. Visible light was never going to be enough. The dust responsible for the zone of avoidance simply absorbs and scatters too much of it. But two other kinds of observation, developed and refined through the 1990s and 2000s, could see through the same dust almost as if it were not there. The first came from radio astronomy. Neutral hydrogen atoms, the simplest and most abundant element in the universe and the dominant raw material inside every galaxy's gas disk, emit a very faint signal at a wavelength of about 21 centimeters, produced by a tiny quantum flip in the atom's electron. That wavelength is far longer than the size of an interstellar dust grain, and light behaves very differently depending on how its wavelength compares to the size of whatever it is passing through. Dust grains that block visible light almost completely let 21 centimeter radio waves through nearly unaffected. A radio telescope tuned to that wavelength can detect a hydrogen-rich galaxy sitting directly behind the thickest part of the Milky Way's disk as easily as one sitting in open sky, because for radio waves at that wavelength, the Milky Way's dust is close to transparent. Astronomers built entire survey programs around this fact. Through the 1990s and into the 2000s, teams including the South African-based astronomer René Kraan-Korteweg systematically pointed radio telescopes and, where the dust thinned enough, near-infrared cameras directly into the zone of avoidance, cataloguing galaxy after galaxies that had simply never appeared in any earlier visible light survey. Near-infrared light with a wavelength longer than visible light but shorter than radio waves offered a middle path, still partially blocked by the thickest dust, but able to see through the thinner, more typical patches well enough to reveal galaxies visible light surveys had missed entirely. Combined efforts, later formalized in dedicated programs, mapped out thousands of previously unknown galaxies, precisely in the region the peculiar velocity studies had implicated. What emerged was not a single dramatic revelation but a slow filling in, galaxy by galaxy, of a map that had previously been almost entirely blank. Where earlier catalogues had shown a conspicuous gap running along the plane of the Milky Way, the new surveys showed that the gap held ordinary galaxies in ordinary numbers, some of them gathered into groups and clusters, just as dense as those found anywhere else in the nearby universe. The dust had never actually removed anything from existence. It had only removed it from view. Once astronomers had tools that did not depend on visible light, the hidden region behind the Milky Way's disk turned out to be exactly as populated, and in places considerably more crowded than the open sky around it. Even with these new tools, mapping the zone of avoidance was slow, painstaking work. Radio surveys covering wide areas of sky at the sensitivity needed to detect faint, distant galaxies took years to complete and required dedicated telescope time that had to be shared with countless other research priorities. Near-infrared surveys carried their own limitation. They could see fainter through moderate dust, but the very thickest parts of the Milky Way's disk directly along the galactic plane itself remained stubbornly opaque even to infrared light, leaving a narrower, but still real, blind strip that neither method could fully resolve. Astronomers had to accept that no single survey would ever produce a perfectly complete map of the hidden region. They built their conclusions instead from the overlapping, converging picture that multiple independent methods, each strong exactly where another was weak, painted together. Crowded was the operative word. As the radio and infrared catalogues filled in, one particular concentration of galaxies, sitting almost directly in the middle of the region, the earlier peculiar velocity and reconstruction work had pointed toward, stood out from the rest. It was large, it was dense, and its position lined up almost exactly with where a decade of indirect gravitational evidence had said something massive ought to be. For the first time, astronomers were not just inferring a mass from the way galaxies moved around it. They were looking directly at a plausible candidate for at least part of the source. The concentration of galaxies that stood out from the new radio and infrared surveys had a name astronomers already knew, though not the significance they were about to attach to it. Catalogued decades earlier and given the designation Abell 3627, after the astronomer George Abell's landmark survey of rich galaxy clusters, it sat in the direction of the southern constellation Norma, and for that reason came to be called the Norma Cluster. The Norma Cluster is, by any measure, an enormous structure. It contains several hundred individual galaxies bound together by their mutual gravity, embedded in a vast cloud of superheated gas, hot enough to glow brightly in X-rays, that fills the space between them, itself weighing several times more than all the visible stars in the cluster's galaxies combined. Measuring that hot gas gives astronomers one of their most reliable ways to weigh a galaxy cluster. The gas temperature depends directly on how deep a gravitational well it is sitting in, since only a sufficiently strong gravitational pull can hold on to gas moving that fast without letting it escape. The Norma cluster's gas temperature places its total mass, including the invisible dark matter that always outweighs the visible material in a structure like this, at something on the order of a few times 10 to the 15th solar masses, roughly 1,000 trillion times the mass of the Sun. Its position mattered as much as its size. Once its distance was measured with reasonable confidence, at approximately 220 million light-years from the Milky Way, it placed the Norma cluster almost exactly where the earlier reconstructions of peculiar velocity flows had located the low point of the gravitational basin the Seven Samurai had first identified. At the time that light now reaching Earth's telescopes left the Norma cluster, Earth's continents were still joined together into the single vast landmass geologists call Pangaea, and the earliest true dinosaurs had only just begun to appear in the fossil record. For a structure that far away and that old in cosmic terms to line up this closely with a gravitational anomaly, first inferred purely from galaxy motions, felt to many astronomers like exactly the confirmation the field had been waiting for since 1988, a real, physical, directly observable mass sitting precisely where an invisible one had been predicted to exist. But the Norma cluster came with an immediate complication, as astronomers refined estimates of both its mass and the total mass required to produce the peculiar velocity flow the Seven Samurai, and later reconstructions had measured, the numbers did not fully match. The Norma cluster, for all its genuine size, appeared to account for perhaps a fifth to a third of the total gravitational pull the data demanded. It was a major piece of the puzzle. It was not, on its own, the whole answer. That left two possibilities open. Either the mass estimates for the surrounding region, or for the cluster itself, contained errors large enough to close the gap once corrected, or the Norma cluster was only the most visible member of something considerably larger, a structure whose remaining mass was spread across a wider volume of space, in smaller groups and clusters still difficult to fully catalogue even with the improved surveys. Both possibilities would turn out to matter. But the second one, that the true scale of the Great Attractor extended well beyond a single cluster, however impressive, would prove to be the more important thread to follow. A single galaxy cluster, however large, rarely exists in true isolation. Clusters tend to cluster themselves, gathered into larger, looser associations called superclusters, bound together less tightly than the individual clusters within them, but still linked by gravity across tens of millions of light-years. Once astronomers accepted that the Norma cluster alone could not supply the full mass the peculiar velocity data demanded, the natural next step was to look for its neighbours, other concentrations of galaxies sharing the same general region of space, hidden by the same stretch of obscuring dust. They did not have to look far. Just beyond the Norma cluster, at a comparable distance from the Milky Way, sits another substantial cluster catalogued as Abell 3T526, commonly called the Centaurus cluster, itself massive enough to register clearly in X-ray surveys of hot intracluster gas. Further out, other groups and smaller clusters, given names like Pavo and Indus after the constellations they sit within, filled in still more of the picture, each contributing its own share of gravitating mass to the same general basin of space. Together, this collection came to be known among astronomers as the Norma Centaurus Pavo-Indus Supercluster Complex, an unwieldy name for what amounted to the real physical answer underlying the plain phrase Great Attractor. Not one object, but an entire loosely bound family of clusters occupying the same enormous stretch of space, largely hidden behind the Milky Way's disk, working together to produce a single coherent gravitational pull. X-ray astronomy did much of the heavy lifting in filling out this picture. The German-led Rorschach satellite, launched in 1990, surveyed the entire sky for X-ray emission, the telltale signature of gas heated to millions of degrees by a deep gravitational well, and its data revealed additional clusters in the Great Attractor region that optical and even infrared surveys had missed or undercounted. X-rays, like radio waves, pass through interstellar dust with far less difficulty than visible light, which made ROSAT and later X-ray missions an unusually effective tool for completing a census of hidden mass specifically in a region defined by its own obscurity. A second, entirely independent method added further confidence to the growing mass estimate. When light from a very distant background galaxy passes close to a massive foreground object on its way to Earth, the foreground object's gravity bends that light slightly, an effect predicted by Einstein's general theory of relativity, and now routinely observed, called gravitational lensing. The degree of bending depends only on the total mass of the foreground object, whether that mass glows, absorbs light, or does neither. Applying this technique to clusters in and around the Great Attractor region gave astronomers a mass estimate that did not depend at all on measuring galaxy speeds or gas temperatures, and it agreed, within the uncertainties, with the dynamical and X-ray based numbers already in hand. Adding together every method and every known cluster in the region brought the total estimated mass of the Great Attractor complex to something in the range of several times 10 to the 16th solar masses, tens of thousands of times the mass of the Milky Way, spread across a volume of space roughly 100 million light-years across. That figure finally closed most of the gap between what had been observed directly and what the original peculiar velocity measurements had demanded back in 1986. The gravitational pull steering the local group and its neighbours was real. It had a location, and now for the first time it had a mass budget that roughly balanced. What it did not yet have was a clear sense of its own limits, whether the Norma Centaurus Pavo-Indus complex was itself the whole story, or merely the nearest and most visible piece of something that extended even further into the dust-obscured distance. Long before anyone had heard the phrase Great Attractor, the American astronomer Harlow Shapley had already noticed something unusual in the direction of the constellation Centaurus. In the 1930s, cataloguing the distribution of galaxy clusters across the sky by hand, Shapley found an especially dense concentration in that part of the heavens, far richer than the surrounding regions. For decades the observation sat mostly as a curiosity, a dense patch on an old catalogue, until astronomers studying the Great Attractor's own gravitational reach in the late 1980s went looking for what lay beyond it, and rediscovered Shapley's dense patch with new instruments and a new question in mind. What they found is now called the Shapley Supercluster, or sometimes the Shapley concentration, and by any reasonable measure it dwarfs the Great Attractor complex itself. Sitting at a distance of roughly 500 to 650 million light-years, more than twice as far from the Milky Way as the Norma cluster, the Shapley supercluster contains more than 8,000 individual galaxies, organized into dozens of separate clusters, bound loosely together across a region of space several hundred million light-years wide. It is, by most estimates, the single largest concentration of galaxies within a billion light-years of Earth, considerably more massive than the entire Norma Centaurus Pavo-Indus complex closer to home. Its size raised an intriguing and still not fully settled question. If gravity from the nearer complex was strong enough to visibly steer the Milky Way and its neighbours off the smooth path of cosmic expansion, could gravity from something even larger, sitting further along essentially the same line of sight, be doing something similar to the nearer complex itself? Several research groups, beginning with work by Somet Ray-Chaudhuri and Roberto Scaramella in 1989, argued that at least part of the flow originally attributed entirely to the Great Attractor might actually be a combination of two effects layered together: a genuine, more local pull from the Norma Centaurus Pavo-Indus complex, plus an additional, longer-range pull from the far larger Shapley supercluster beyond it, both acting in roughly the same direction and therefore difficult to fully separate using peculiar velocity data alone. This picture remains debated, and it should be treated as such. Untangling the relative contribution of two gravitating structures lying along nearly the same line of sight, at very different distances, is a genuinely difficult measurement problem, and different research teams analysing overlapping datasets have reached somewhat different conclusions about exactly how much of the Milky Way's motion traces to the nearer complex versus the more distant supercluster. What is not seriously disputed is that Shapley's gravity reaches a very long way. Some large-scale reconstructions of the local peculiar velocity field extend Shapley's gravitational influence out across hundreds of millions of light-years, potentially making it, rather than the originally identified Great Attractor, the single largest gravitational influence on large-scale galaxy motions within reach of current surveys. There is a certain fitting irony in the story bending this way. The object first given a name specifically because it seemed to be the source, the attractor, itself turned out to be sitting inside the gravitational reach of something even larger and further away, itself presumably influenced by still more distant structures, beyond current instruments' ability to measure with confidence. Every time astronomers thought they had found the bottom of this particular gravitational well, a wider and deeper one turned out to lie just past the edge of what could be clearly seen. That pattern, structure nested inside structure, each one larger than the last, is not a peculiarity of this one corner of the universe. It is, as the next chapter follows, close to the general rule for how matter arranges itself across the whole of the observable cosmos. Step back far enough, and the universe stops looking like a random scatter of galaxies and starts looking like something closer to a sponge or a web. Large surveys that map the three-dimensional positions of hundreds of thousands of galaxies, built up over the past several decades, consistently reveal the same overall pattern. Galaxies cluster along long, thread-like filaments, sometimes hundreds of millions of light-years in length, which intersect at especially dense nodes containing clusters and superclusters like the ones behind the Great Attractor and the Shapley Supercluster. Between the filaments lie enormous, comparatively empty regions called voids, tens to hundreds of millions of light-years across, where galaxies are scarce and spaces on the largest scales that still show clear structure, close to featureless. Astronomers call this overall arrangement the cosmic web, and it is now understood to be the basic architecture of matter across the observable universe. The cosmic web did not spring into existence fully formed. It grew over roughly 13.8 billion years from almost imperceptibly small differences in the density of matter present in the universe's first fraction of a second, differences amplified enormously by an extremely rapid early expansion physicists call inflation. Regions that started out just fractionally denser than their surroundings exerted very slightly more gravity, which drew in slightly more matter, which increased their gravity further still, a slow self-reinforcing process that continued, largely unbroken, for billions of years. Slightly denser regions grew into filaments and eventually into the massive clusters and superclusters found at the densest nodes of the web today. Slightly less dense regions, meanwhile, emptied out further as gravity drew their matter toward the denser filaments nearby, hollowing them into the voids observed today. Dark matter, again, did most of the structural work. Because dark matter dominates the total mass of the universe by roughly 5-to-1 over ordinary matter, and because it interacts with almost nothing except through gravity, computer simulations show it assembling into the filament and void skeleton of the cosmic web first, essentially unimpeded by the friction, radiation pressure, and collisions that slow down ordinary gas. Ordinary matter, the hydrogen and helium that would eventually form stars and galaxies, followed the dark matter's gravitational lead afterward, falling into the same filaments and pooling at the same nodes, like water finding the low points of a landscape that had already been carved out by something else entirely. Seen against this backdrop, the Great Attractor complex and the far larger Shapley supercluster beyond it are not unusual exceptions to how the universe is arranged. They are simply two especially prominent nodes in the local section of the cosmic web, denser knots where several filaments happen to converge, exactly the kind of location the web-building process predicts should host the largest galaxy clusters. To put the scale in perspective, if the entire portion of the universe observable from Earth were shrunk down to the size of a single country, the cosmic web's largest filaments would appear as a sparse network of roads only a few kilometers wide, and the voids between them would be vast stretches of open countryside making up nearly all of the remaining land. Galaxies, including the Milky Way, sit almost entirely along the thin roads, never in the empty countryside between them. This reframing changes what a phrase like Great Attractor actually means. It is not a single, uniquely mysterious object waiting to be fully unmasked. It is a name given, before the full picture was understood, to one especially significant intersection in a structure that spans the observable universe, built the same way everywhere: gravity, acting patiently over cosmic time, on ripples set down in the universe's earliest moments. Understanding that structure at the scale relevant to the Milky Way's own motion would require one more step: mapping not just the clusters themselves, but the full three-dimensional pattern of how every nearby galaxy is flowing through the web that connects them. Confirming a structure's existence and precisely mapping its shape are two different achievements, and the second took considerably longer than the first. Through the 1990s and 2000s, various individual surveys had measured peculiar velocities for hundreds, then thousands, of galaxies scattered across different parts of the sky, using different distance measuring techniques suited to different types of galaxies. Each survey on its own gave a partial, patchy view. What the field needed was a single, unified dataset built by carefully combining every reliable individual distance measurement into one consistent three-dimensional map of how galaxies across the nearby universe were actually moving. That project fell largely to the astronomer Brent Tully and a growing international collaboration working over more than 2 decades under the name Cosmic Flows. Rather than developing one single new distance measuring technique, The Cosmic Flows team combined results from several established methods, including the same kind of elliptical galaxy relation the Seven Samurai had used, together with distance measurements based on the intrinsic brightness of certain pulsating stars and the properties of spiral galaxy rotation, carefully cross-calibrating each method against the others, so the combined dataset behaved as one coherent whole rather than a patchwork of incompatible pieces. By the project's later stages, Cosmic Flows catalogues included accurate distance and velocity measurements for tens of thousands of individual galaxies, reaching out across hundreds of millions of light-years in every direction. With a dataset that large and that well-calibrated, Tully's team could do something the earlier reconstructions had only approximated: trace the actual three-dimensional velocity vector of each galaxy, the direction and speed each one is truly moving through space, once the smooth cosmic expansion is subtracted away, and follow those vectors like arrows across a map. Where the arrows converge, gravity is winning, pulling galaxies together toward a common low point. Where the arrows diverge, spreading apart from a common origin, something closer to a void is pushing galaxies apart as its own emptying process continues. Astronomers borrowed a term from terrestrial geography to describe the resulting pattern. Just as a river drainage basin on Earth collects rainfall from a wide surrounding area and channels it toward a single low point, a basin of attraction in this cosmic sense collects galaxies from a wide surrounding volume of space and channels their motion toward a single gravitational low point, a watershed for matter instead of water. Applying this framework to the full Cosmic Flows dataset produced something genuinely new, not just confirmation that the Great Attractor complex existed, but a clear picture of exactly how large a volume of space was gravitationally connected to it, following the true convergence of thousands of individual velocity vectors, rather than inferring a rough direction from a smaller sample. The basin turned out to be considerably larger than the original Seven Samurai study, working with a few hundred galaxies, could ever have shown. It extended across hundreds of millions of light-years, encompassing not only the Milky Way's local group, but a great many other groups and clusters, previously thought to belong to entirely separate structures. The Great Attractor itself, in this fuller picture, no longer looked like the single ultimate destination of the flow. It looked instead like a saddle point, a low ridge partway down a much larger basin, a place where the terrain briefly levels out, before continuing to slope downward toward the deeper concentration represented by the Shapley Supercluster further beyond. Tully's team gave the entire basin, the whole watershed of galaxies all flowing, directly or indirectly, toward this shared gravitational low ground, a name of its own, one that would finally place the Milky Way's own galaxy within a home structure far larger than anyone had previously mapped in such careful detail. In September 2014, Tully's team published the result of that mapping effort in the journal Nature, and with it introduced a name that immediately reframed how astronomers, and eventually the wider public, thought about the Milky Way's place among the galaxies. Laniakea, a Hawaiian word meaning immense heaven, chosen deliberately to honor the tradition of Polynesian navigators who once crossed the vast Pacific horizon, guided only by the stars the horizons, and an intimate knowledge of the currents beneath their boats. Laniakea is the name given to the entire basin of attraction the Cosmic Flows data revealed, a supercluster of galaxies spanning roughly 500 million light-years across its widest extent, containing an estimated 100,000 individual galaxies with a combined mass, including dark matter, of roughly 10 to the 17th solar masses, on the order of 100,000 trillion times the mass of the Sun. Every galaxy within this vast volume, including the Milky Way, the local group, the Virgo cluster near the center of the supercluster, and the more distant Norma Centaurus Pavo Indus complex, shares a common gravitational destiny, all of their individual peculiar velocities pointing, directly or by way of a longer curving path, toward the same shared low point in the overall gravitational terrain. That low point is the Great Attractor. In Laniakea's finished map, the region first identified by the Seven Samurai in 1986 sits close to the gravitational center of the entire supercluster, the deepest and most significant point of convergence within Laniakea's boundaries, the valley floor toward which the whole basin's contents are slowly draining. The comparison to a terrestrial watershed, introduced loosely in the previous chapter, turns out to describe the physical reality with real precision. Just as every raindrop falling anywhere within a river's drainage basin eventually finds its way, directly or through a long chain of smaller tributaries, to the same river mouth. Every galaxy within Laniakea's roughly 500 million light-year boundary is, in a slow gravitational sense, one drop of water in the same basin. All of it, eventually, headed toward the same shared destination at the Great Attractor's location. The driftwood carried along the current, an image reached for earlier to describe individual galaxies caught in the flow, was never drifting aimlessly. It was following the actual contour of a very large, very real gravitational landscape, one that took nearly 3 decades of astronomy, across multiple independent methods, to finally trace from source to destination. Laniakea's boundary is not an arbitrary line drawn for convenience. Tully's team defined it precisely where the velocity flow pattern changes character. Inside the boundary, galaxy velocity vectors converge toward the Great Attractor. Immediately outside it, in the direction of the neighbouring Perseus-Pisces supercluster, the vectors instead converge toward a different separate gravitational centre. Laniakea's edge is, in that sense, a genuine watershed divide, the same kind of boundary that separates one river's drainage basin from its neighbour on a terrestrial map, except drawn here in 3-dimensional space, across hundreds of millions of light-years, using the true motions of tens of thousands of galaxies rather than the flow of rainwater across a hillside. Placing the Milky Way within this structure answered, in the most complete way, astronomy has yet managed, the original question the cosmic microwave background dipole and the Rubin-Ford peculiar velocity measurements had raised decades earlier. We are moving at roughly 2.2 million kilometers per hour, not because of some anomalous, unexplained force acting on our galaxy alone, but because the Milky Way sits, like 100,000 other galaxies, well within the gravitational reach of Laniakea's Basin, following the same slow current toward the same shared low point that every other galaxy in the supercluster is following as well. The mystery had not merely been solved, it had been placed inside a far larger and far more coherent picture of the universe's structure than anyone chasing a single anomalous motion in 1976 could have anticipated. Not every large-scale flow claimed in the scientific literature has held up as well as Laniakea's mapped basin, and an honest account of this story includes the ones that remain genuinely unresolved. In 2008, the astrophysicist Alexander Kashlinsky and collaborators published an analysis of several hundred distant galaxy clusters using X-ray data combined with measurements of the cosmic microwave background, the same relic radiation whose small temperature variations first revealed the Milky Way's own motion decades earlier. Kashlinsky's team reported that these distant clusters, many of them far beyond the reach of Laniakea's or even Shapley's gravitational influence, appeared to share a small but consistent bulk motion, several hundred kilometers per second, all pointing in a broadly similar direction, one that partially overlapped with the general direction of the Centaurus constellation already familiar from the Great Attractor story. The claim, which the team termed dark flow, was provocative precisely because the clusters involved were, according to standard cosmological models, too far apart and too distant from any known concentration of mass to be gravitationally influenced by anything within the observable universe strongly enough to produce a shared, coherent motion of that kind. If the result held up, it would suggest one of several dramatic possibilities: an enormous, still undetected mass concentration lying just beyond current instruments' reach, a large-scale asymmetry left over from the universe's very earliest moments, potentially even the imprint of structures that existed before or during cosmic inflation, effectively outside our entire observable universe, or, more plainly, a subtle systematic error in how the underlying X-ray and microwave background data were being combined and analysed. The response from the wider cosmology community was, appropriately, cautious. Several independent groups attempted to reproduce the dark flow signal using the same or similar cluster catalogues and found the result considerably weaker or statistically indistinguishable from noise once different analysis choices were applied. The European Space Agency's Planck satellite, which mapped the cosmic microwave background with far greater precision than the earlier WMAP data Kashlinsky's original analysis had relied on, published its own investigation in 2013 and found no significant evidence for coherent bulk flow extending to the distances the original dark flow claim required. That result substantially weakened, though it did not entirely eliminate, the case for dark flow as originally proposed. Most cosmologists working in this area today treat the phenomenon as an interesting but unconfirmed claim one that would require considerably stronger and more consistent evidence across independent datasets before it could be accepted as a genuine feature of the universe, rather than a statistical artifact of a difficult measurement. The dark flow episode is worth including in this story for what it illustrates about how this entire field actually works, not despite its uncertain outcome, but because of it. The same basic method, comparing measured galaxy or cluster motions against the smooth expectation of cosmic expansion that correctly and repeatedly confirmed the existence of the Great Attractor and eventually Laniakea, can also produce claims that later analysis fails to confirm. Good science in this area depends on exactly the kind of scrutiny that dark flow received. Independent teams re-examining the same evidence, applying different assumptions, and being willing to report when a striking initial result does not survive closer inspection. The Great Attractor earned its place in the accepted scientific record because it passed that test repeatedly across nearly 3 decades and multiple independent lines of evidence. Dark flow so far has not, and honest science reports that difference rather than treating every provocative claim as equally established. Every structure in this story, the Norma Cluster, the Shapley Supercluster, the entire Laniakea Basin and the cosmic web that connects it to its neighbours, traces its origin back to something almost absurdly small: quantum fluctuations, tiny random variations in the density of matter and energy, present in the universe within its first fraction of a second of existence, on scales far smaller than a single atom. According to the leading cosmological model, an extremely rapid early episode of expansion called inflation stretched those microscopic fluctuations to enormous size almost instantly, transforming quantum-scale randomness into the seeds of every large-scale structure that would eventually form. Those seeds left a visible fingerprint in the cosmic microwave background, the same relic radiation whose overall dipole pattern first revealed the Milky Way's own motion in this story's opening chapter. Look past the dipole at the much finer variations in the background radiation's temperature across the sky, mapped with steadily increasing precision by the COBE, WMAP, and Planck space telescopes between 1992 and the 2010s, and a pattern of tiny hot and cold spots appears, differences of only a few parts in 100,000, corresponding to the same primordial density fluctuations from the universe's earliest moments, captured at the instant, roughly 380,000 years after the Big Bang, when the universe first became transparent enough for that light to travel freely. Every structure that exists today began as one of those faint spots. Gravity did the rest of the work, but it needed a very long time to do it. A region of the early universe only slightly denser than average exerted very slightly stronger gravity on the matter around it, drawing in a little more material, which increased its gravity a little further in a slow, self-reinforcing process astronomers call gravitational instability. Left to run for hundreds of millions, then billions of years, that process turned barely perceptible density differences into the dramatic large-scale structure observed today. Filaments hundreds of millions of light-years long, dense nodes hosting massive clusters like Norma and Shapley, and enormous voids where the earliest fluctuations happened to run below average in gravity, over cosmic time, drained what little matter was there into the surrounding filaments instead. Dark matter, unable to interact with light or with itself except through gravity, assembled into this skeleton first and fastest, since it faced none of the friction, pressure, and radiation effects that slowed down the ordinary gas that would eventually form stars and galaxies. Modern computer simulations, tracking the gravitational evolution of billions of simulated dark matter particles across the age of the universe, reproduce the observed cosmic web, its filaments, its nodes, its voids, its great attractors and Shapley superclusters with striking fidelity when they start from the exact pattern of density fluctuations the Planck satellite measured in the cosmic microwave background. That agreement between a snapshot of the universe at 380,000 years old and the structure observed 8 billion years later stands as one of modern cosmology's most thoroughly tested and best confirmed results. Seen from this vantage, the Great Attractor is neither an anomaly nor a coincidence. It is one particular unusually well-studied outcome of a single universal process, quantum fluctuation amplified by inflation, then sculpted by billions of years of gravity, that produced every structure in the observable universe, including the Milky Way itself, including the Sun, including, at the very end of a very long causal chain, every listener learning this story for the first time. The next question is not how such a structure could have formed, it is what becomes of it, and of the Milky Way's place inside it, as the universe continues to age. Every galaxy's fate divides broadly into two very different categories, and which category applies depends entirely on whether gravity has already succeeded in binding it to its neighbours. The Milky Way and the Andromeda Galaxy, along with several dozen smaller galaxies, form the local group, a structure gravity bound together long ago and firmly enough that the ongoing expansion of the universe has no effect on it at all. Andromeda is currently approaching the Milky Way, not receding with the rest of the universe, and current models predict the two galaxies will begin merging in roughly 4 to 5 billion years, a slow collision unfolding across hundreds of millions of years rather than a single dramatic event, eventually producing a single larger galaxy, sometimes informally called Milkomeda. Bound systems like the local group are not going anywhere. Whatever else happens to the wider universe around them, their internal gravity has already won. The relationship between separate superclusters is a different story entirely, and it is where the accelerating expansion of the universe, driven by the mysterious component cosmologists call dark energy, eventually changes the picture painted throughout this story. Since the late 1990s, observations of distant exploding stars called supernovae have shown that the expansion of the universe is not merely continuing, it is speeding up, with space itself stretching at an ever-increasing rate. On the scale of the local group, bound tightly by gravity, that accelerating stretch makes no measurable difference. On the scale of the roughly 500 million light-year gap between separate superclusters like Laniakea and its neighbours, it matters enormously, because gravity's pull weakens with distance, while dark energy's effect grows stronger the more space there is to stretch. Current cosmological models suggest that, over a timescale of tens of billions of years, considerably longer than the roughly 13.8 billion years the universe has existed so far, the accelerating expansion will increasingly dominate over the comparatively gentle gravitational pull connecting Laniakea to more distant structures like the Shapley supercluster. The flow this entire story has traced, from the Milky Way's fall toward the Great Attractor, to the Great Attractor's own position within Laniakea's larger basin, to Laniakea's gravitational connection toward Shapley beyond it, would not reverse or suddenly stop. It would simply matter less and less, as the space separating these superclusters stretches at a rate gravity increasingly cannot keep pace with. Galaxies deep within Laniakea's own basin, including the Milky Way, would likely continue drifting slowly toward the Great Attractor's general vicinity, since that pull operates at a scale gravity can still dominate. But Laniakea's own weak gravitational thread connecting it to Shapley and to still more distant superclusters would, over these very long timescales, effectively snap, leaving each supercluster to continue evolving as an increasingly isolated island, unable to influence or even, eventually, to observe its neighbours as the accelerating stretch of space carries them beyond each other's cosmic horizon. Every part of this projection deserves the same caution given to any forecast reaching tens of billions of years into the future. It rests on the assumption that dark energy's behaviour, currently modelled as a constant density filling space uniformly, continues unchanged across a span of time more than 7 times longer than the universe has existed to date, an assumption current data supports but cannot fully confirm this far ahead. Astronomers hold this picture with appropriate confidence for the physics involved, while remaining honest that any model projected this far into the future carries real uncertainty. What the evidence gathered so far does support with considerably more confidence is the shape of the story already told, a real, measurable gravitational structure, mapped patiently over nearly 4 decades, that is currently, at this moment, still carrying the Milky Way and everything in it along a genuine physical current through space. Return for a moment to where this story began, a faint hiss in a New Jersey antenna, a tiny warm and cool tilt across the oldest light in the universe, and a single number, 2.2 million kilometers per hour, describing a motion nobody at the time could explain. Nearly 40 years of work by radio astronomers, X-ray satellites, infrared surveys, and patient distance measurements to tens of thousands of individual galaxies stand between that first puzzling observation and the picture available today. The Milky Way is a minor member of Laniakea, an immense supercluster spanning roughly 500 million light-years and containing on the order of 100,000 galaxies, all gently converging across a timescale of billions of years toward a shared gravitational low point still carrying the plain, unglamorous name astronomers gave it back in 1986, the Great Attractor. The dust that once made this entire story so difficult to uncover, the zone of avoidance running along the plane of our own galaxy, never actually hid the universe from existing. It only ever hid it from a particular kind of light, the kind human eyes and early telescopes happened to be built to use. Once astronomers learned to look with radio waves and infrared light instead, the supposedly empty band of sky turned out to be exactly as full of galaxies, clusters and structure as anywhere else, arranged along the same filaments and gathered at the same nodes that define the cosmic web everywhere in the observable universe. The lesson generalizes well past this one patch of sky. An absence of evidence in astronomy as much as anywhere else is very often just an absence of the right instrument. The driftwood image reached for earlier to describe the Milky Way's slow motion through the flow toward the Great Attractor holds up as well as any single metaphor can for something this large. Every galaxy caught in Laniakea's Basin, our own included, drifts along a current shaped not by any single dramatic force but by the accumulated, patient pull of gravity acting across hundreds of millions of light years and billions of years of time, following contours laid down in the universe's first fraction of a second and only fully mapped in the last decade. No galaxy in that current feels a sudden tug, or notices any change from one human lifetime to the next. The motion is entirely real and entirely imperceptible at any scale a single observer, or even a single civilization's recorded history, could ever directly sense. That combination, a motion both completely real and completely undetectable, without decades of careful, cumulative science, is perhaps the truest thing this story has to offer. The Milky Way is not moving toward the Great Attractor because anything is wrong, or because anything unusual singles our galaxy out. It is moving because every galaxy nearby is doing the same thing, all of us caught in the same basin, tracing the same current, shaped by the same structure that gravity has been quietly building since a fraction of a second after the universe began. Discovering that motion took a chance detection of leftover radiation from the Big Bang, a team of 7 astronomers willing to name a mystery before they could explain it, and nearly 4 decades of patient work finding new ways to see past our own galaxy's dust. What it found, in the end, was not a hidden threat waiting in the dark behind the Milky Way's disk, but a far larger home than anyone had previously mapped, and a quiet, ongoing reminder that the universe we can see directly is only ever a fraction of the one we actually live inside. The Great Attractor turned out to be less a destination than a signpost. What began as an unexplained wobble in the motion of our own galaxy led, across nearly 40 years of careful observation, to the discovery that the Milky Way belongs to something far larger than itself. Laniakea, a supercluster of 100,000 galaxies, bound together by gravity built from ripples set down in the universe's first fraction of a second. The Great Attractor sits near the gravitational heart of that structure, the low point in a basin our own galaxy has been quietly falling toward, at 2.2 million kilometers per hour, since long before there was anyone on Earth to measure the fall. Even that picture, astronomers now suspect, is not the final word. The Shapley supercluster looms larger still beyond it, and the accelerating expansion of the universe will, over tens of billions of years, eventually loosen even Laniakea's own gravitational grip on its most distant members. What remains constant is the method more than any single answer: patient measurement, independent confirmation, and a willingness to be wrong before being right. The universe did not owe anyone an easy view of its own structure. It took nearly 4 decades of looking past our own galaxy's dust to see even this much of it clearly, and the picture is, almost certainly, still incomplete.